All right, what's up, everybody? Welcome back to Structure Free Chicka Chicka Learning. And in this video, we're going to derive the slope deflection equations, which are circled in this orange cloud bubble here. You don't even have to know what any of these variables are right now. But by the end of this video, hopefully you'll have an understanding of where this equation comes from and what role it plays in a displacement-based method of structural analysis. Quick recap on what a displacement method of structural analysis is. So a displacement method of structural analysis involves identifying the degrees of freedom and being able to write the associated equilibrium equations with each degree of freedom. The other part of a displacement method involves you writing load displacement equations. And what these do are just relate the internal loading that might happen on a member to the actual displacement of the member. And what you do is you take these load displacement relationships, substitute them into the equilibrium equations, and from there you will be able to calculate displacements first. Once you have the displacements, you plug them back in to your load displacement relationships, and you have your internal loads. And after you get your internal loads, you can draw shear moment diagrams, calculate stresses, do all kinds of design. A critical part of using a displacement method of analysis is this load displacement relationship. And in physics, you've seen load displacement relationships. Like in physics, your first most basic load displacement relationship was for a spring, and you had F equals kx, right? And here it related the internal force in the spring to the displacement of the spring. Maybe you even use the symbol delta instead, like this. But that is a load displacement relationship right there. And so we need that for the members that build the structures that we design and analyze, which are essentially beam elements or beam members, or what we connect together to make a structural system. All right, so to derive the slope deflection equations, which are central to the slope deflection method because they provide our load displacement relationships that we need, we are going to consider this continuous member between A and B, which has a constant EI. And it's got some loading. It can be any loading that you want on the member, but here for purposes of illustration, I'll just draw a uniformly distributed load. But it could be a concentrated load, it could be non-linear, it can be linearly varying. You could have any sort of loading on the member between A and B. And what I'm trying to do is relate the internal end moments that could be happening here and here to the unknown displacements. And there are three unknown displacements. The unknown displacements are a slope or rotation at A, the slope or rotation at B, and then I can have a linear displacement, which just means like point A could go up or down, and let's say down due to settlement, and point B could go up or down. And what I would have is what I'll call a relative displacement between B and A. The symbol delta represents a relative linear displacement between B and A. All right, so since we're deriving a relationship here, we need some sort of sign convention. For the slope deflection equations, our sign convention is based on the direction of rotations. And so we'll say that any rotation that is associated with a clockwise motion is positive. So to illustrate that, let's start with the relative linear displacement between B and A. So if I have a member originally here, this original member here, let's say that I cut this out, and it's possible that end A would move down a certain distance. I'll call this delta A. And delta B moves another distance, which happens to be bigger, delta B, like this. And now the member has rotated into this final shape. Based on its settlement, it looks like this. So each ends A and B, if I'm just considering those only, it would look like this. The original shape here, if I draw the horizontal line here, originally it was horizontal like this. And because the member rotated clockwise from its original shape, we'll call this psi. This psi is called the chord rotation, and because it was clockwise, it is positive. And it's related to these linear displacements. And this chord rotation would be equal to this relative deformation delta. Delta here would be delta B minus delta A. And this chord rotation would be this delta over L. So the way that I've drawn the chord rotation, this looks like a rigid body rotation, as in there's no deformation of the member. The member stays, if you will, rigid, and so it just does a rigid translation and rotation to get to where it's at. So my chord rotation is positive clockwise with respect to the original position of the member. Then if I introduce a slope or rotation of the member at A, it would look like this. And then a clockwise rotation at B, I'd have this exaggerated deformed shape. The slope at this point, this would represent theta A, and the slope here relative to a horizontal would be a positive theta B. So these are my positive deformations or rotations expressed on the member. And so now, if I look at the shape, the deformed shape of my member, this dotted blue line, I'll notice that I have a concave up region on the left side or near the left right here, and that would indicate that I have compression at the top, tension at the bottom, and which would be associated with an internal moment that goes like this. And then on the right side of my member, I have compression on the bottom and tension on the top, which would be associated with an internal moment that goes like this. And these would be my end moments. This one on the left I'll call my end moment at AB, and this would be my end moment BA. And what I want to do now is relate each of these internal moments to the deformations or the rotations, to this chord rotation, to the slope at A and the slope at B. This means my end moments are positive clockwise. And more importantly, whenever you use the slope deflection equations, you just have to remember that a positive result means a clockwise end moment, and it's going to be a different sign convention or internal load convention when you go to draw the shear moment diagrams. That's usually the biggest mistake between translating the answers that you get from the slope deflection equations into drawing normal shear and moment diagrams of your member or your frame or whatever it is that you're trying to analyze. And so now what we want to do is relate the member end moments to each of these displacements or rotations. And now we're going to determine the slope deflection equations by evaluating one displacement at a time by the principle of superposition. And what we'll do is we'll write the relationship or derive the relationship between the end moments MAB and MBA with theta A, theta B, and delta or psi, which is essentially the chord rotation delta over L, one at a time. Okay, so the first thing that we're going to do, we're going to look at as if we only have the rotation theta A or slope theta A, and everything else is held at 0. Everything else, theta B is 0 and delta is 0. And so what would that look like? And for us, that structure would look like we have no relative displacement. So that means the member is going to be horizontal. Yes. This and end B has no slope. So that means that would be like a boundary condition where the structure is fixed at end B. At end A, again, I can't move up or down, but I can rotate. And so that would be like having a pin or roller support at A. And if I enforce or exaggerate a displacement, theta A, my deformed shape of the structure would look like this. And you'll notice that theta A here is in the positive clockwise direction. Yes. So if I have this rotation, theta A, and I cut out the member, the moments associated with this deformed shape should look something like this. And based on the deformed shape, I should expect an end moment on the left here to have compression at the top and tension at the bottom, which would look like this. And here, this segment, there's a point of inflection somewhere along the length of the member. And here, from the inflection point to B, my member is concave down, meaning I have compression at the bottom and tension at the top, which is associated with the moment that looks like this. And I'll call that MBA. And there's no rule for the shears at the end of the member, so I just follow what I normally do, which is on this side of the cut, I will have it going up, VAB. This is the end shear, VAB, and then here I have a shear VBA like this. And now what I want to do is really get a moment diagram in terms of MAB and MBA. And once I have a moment diagram, I can create a curvature diagram, and then I can use all manners of methods to determine the slope at A in terms of MAB and MBA. All right. And so what does that mean? What does all that mean, what I just said? Well, first, let's just go ahead and do an analysis where we just want to determine the shear and moment diagram. We're going to treat MAB and MBA as like known values. And we'll have here, if by equilibrium, I can solve for the end shears VAB and VBA. So here, some of the moments about A, and this will tell me VBA is negative MAB plus MBA divided by L. And then from some of the forces in the vertical direction, I would get VAB minus VBA equals 0. And that just tells me that VAB equals VBA, which is negative MAB plus MBA divided by L also. And I could go even further now. I could even draw the shear and moment diagrams in terms of MAB and MBA. So here's the member. I have the end moments, and then I know that the shear at AB from my original drawing is negative MAB plus MBA over L. That negative just means that that shear should point the other direction. And so here I would have a shear force pointing down, which has a magnitude of MAB plus MBA over L, and then equal and opposite on the other side here. And this, now to draw the shear moment diagram, just as before, just like you learned in statics and basic mechanics of materials, when we draw these internal loading diagrams, we're still using the sign convention here, our positive internal loading sign convention. Compression at the top, tension away, normal force, and then a shear up and down like this. That was our positive internal loading sign convention when we draw shear and moment diagrams, and that has not changed. And so here, our shear diagram down goes constant like this. So I have 0 load, it's constant. My shear diagram there, and my moment diagram would start with positive MAB and negative MBA. So I'm going to use the moment diagram to relate the end moments, MAB and MBA, to the slope at A, which is theta A. I'm going to use double integration method, but you can use the conjugate beam method. Shoot, you can use the moment area method, method of virtual work, whatever you want. And for the integration method, what I really need is a moment function. And so I can extract that moment function from the graph if I wanted to. I can also, and I'll take the time to do this, but I can also just do it from a free body diagram from up here, from this thing right here. And I have no load between the ends of the member. So really, I only have two discontinuities. I have a discontinuity at A, a discontinuity at B. I just need one cut to describe this function, the internal moment function. I'll go even more. I'll use a coordinate system from the end at B. The origin will be at B and going right to left. So this will be my coordinate system for the cut. And I will take this drawing and I'll bring it down, this cut out. And here is my free body diagram for that cut between member A, B. I'll have some internal moment that I'm trying to solve for. I'll call that M1. And then there's a shear here. I'll call that V1. All right. And those are my symbols for the moment and shear functions. To get that moment function, I can just sum moments about the cut. So one of the first things you always had to do in the double or the integration method was come up with a moment function so that you can create the curvature function. And the basis of that double integration method was that here you would have this d squared v dx squared, where v is the equation of the elastic curve, and this is related to the curvature m over ei. And again, the idea is that if I integrate twice from there, I can get a displaced shape or elastic curve. So in this case, the moment function by equilibrium of this drawing right here, if I take moments about the cut equal to 0, negative m1 plus from that shear, which is MAB plus MBA over L times X, which is the moment arm, minus MBA right here equal to 0. Check it out. This just tells me M1 is, and this is my moment function. And this is just the equation that represents this moment diagram right here. That's it. That's all it is. No big deal. So I have my moment function. Now I got to integrate twice. And this relationship is the same as this is the moment function right here, this M1. And so if I want the slope function, EI theta of x, this would be an antiderivative of this. So this would be plus a constant. One more integration will give me the equation of the elastic curve essentially, and this would be x cubed over 6 plus c2. Yes. And now to solve for the constants, I got to think about the boundary conditions. And if I go all the way back here to this drawing right here, this right here, where I have the rotation at A and B. Well, I've got several boundary conditions. One, I know the slope at B is 0. I know that the displacement at B is 0, right? There's no vertical deflection, and the slope at B is 0. I also know that I have no vertical deflection at A. And so my boundary conditions, the first two that I will use are that in terms of my coordinate system, this location was x equals 0, and I had x going this way, like this. And so point B actually represents x equals 0, and point A represents x equals L in terms of my integration or my moment function and my integration method. And so in terms of boundary conditions, if I use the boundary conditions at B, this is where x equals 0. I would have the slope at 0 equals, which is the slope at B, is equal to 0, and the displacement at B, which is the displacement at 0, equals 0. Those would be my two boundary conditions. And these tell me, so if I plug in 0 into this equation here, I would get that C1 equals 0. And then once I know that C1 is 0, if I plug in 0 here and I know that my deflection is 0, then I would get C2 is 0, like that. And if you're not sure, I want you to plug it in and just double check it for me. All right, great. So now I know that C1 is 0 and C2 is 0. And so now, hopefully, I can relate my moment for AB and BA to the slope, theta A. And essentially what I have are two unknowns in this case. So MAB is an unknown and MBA is an unknown. And I want to solve for two unknowns. So I'm going to use my other boundary conditions to finally relate MBA. I want to put this as a function of theta A and MAB as a function of theta A, like this. And the two boundary conditions are at A. My boundary conditions at A are as follows. Let's see. Well, at A, my vertical deflection is 0 and my rotation is theta A. And so at x equals L, which is essentially theta A. So theta at L equals theta A, whatever that value is. I don't know. I'm putting it in terms of theta A. My vertical deflection at L, which is my vertical deflection at A, is 0, like this. And so I can use these two relationships. Let's go ahead and use the slope relationship. This first boundary condition would be that EI times theta at L, which is the same as EI times theta A, is equal to, and all I'm doing is substituting L for wherever I have an X. There's one equation, and my other equation will come from the displacement function, which is equal to 0 is equal to. And so let me start with this equation here. This top one, I'll number that 1 and number 2. So if I simplify equation 1, so I'll just do some algebra. I would have this, that would cancel, and I would have, let's see, MAB which becomes MAB L over 2 minus MBA L over 2. And now if I simplify the second equation, the L's would cancel. That's going to be a squared there. And I would have MAB L over 6 plus MBA L over 6 minus, oops, don't forget the squared, minus MBAL squared over 2. And again, if with some algebra here, all the L squareds would cancel out. Ayo, multiply both sides by 6. And I would get MAB like this, and this would tell me that MAB is equal to 2 MBA. And here, again, I'll relabel this as 1, and here is 2. And now all I got to do is combine 1 and 2, and I'll be able to solve for MAB and MBA on their own. So I'll substitute 2 into 1 here. This tells me MBA is equal to 2EI over L times theta A. And MAB is double that, so that's just going to be, if I plug this back into equation 2, this will be 4EI over L times theta A. And so I have a relationship for the moment at the ends of the members with respect to theta A. So a quick recap on what we've done so far. We have these degrees of freedom associated with a member. This delta, the end rotations at A and B, and now we're imposing them one at a time in their positive sense in order for us to relate the end moments AB and BA to each of these displacements or rotations. And for the first one, we allowed the rotation at A, and we held the others to 0. And we're going to go similarly. And this time, for part 2, we're going to apply the rotation theta B as if it's a known value. And we're going to hold the others, theta A and delta, also 0. And again, this results here in a structure that would look like this. And our member stays horizontal because there's no relative displacement. And here, if the slope is 0 and point A will not move up or down, then this will look like a fixed support at A. And here at end B, I will have a rotation, a positive rotation, which is clockwise for the slope-deflection equation sign convention. And so my deflected shape of the member will look right there. And I would have my slope at B, so that we treat like a known displacement right there. And again, we could construct or go through and apply equilibrium, cut out the member. And again, we can cut the member out and draw in the end moments associated with the displaced shape. And very similarly to what we did for theta A, by using the moment function and creating a curvature function, integrating twice, and using the boundary conditions associated with the fixed support at A, I can solve for the slope function for this beam and the displacement function for this beam. And then I can use the boundary conditions at end B. I will be able to determine an equation for the end moments as they relate to the rotation theta B. And my equations, very similar to before, but in this case, MBA will be 4EI theta B over L, and MAB will be 2EI over L times theta. And if you don't believe me, what you should do is try following the same process that we did earlier and use it for this diagram here, for this rotation at theta B. So now I've accounted for two of my rotations. So now we're going to move on to the chord rotation, which is this relative displacement between the ends of the members. And here, part 3 of this derivation is we're going to apply this chord, a positive chord rotation, which is clockwise again. And that means this chord of psi is equal to delta over L. And that means either end A goes up or end B moves down in this chord rotation. And we have to have the slopes at A equal to 0 and the slope at B equal to 0. These constraints I can model as a fixed beam, and I have to have a chord rotation that is clockwise, which means that either end A goes up or end B goes down. Whatever happens will rotate. If it's like this, yes, this displacement delta, and this is my chord rotation psi. So there's actually has to be some sort of deformation. So the slope here has to be horizontal, and the slope here has to be horizontal. And so my beam, the blue line, would show is an exaggerated, deformed shape of the beam, and it would look like this. Yes, like that. And what's more now, if I cut it out, like here, okay, again, this exaggerated, deformed shape. This delta, this settlement is even exaggerated as well. But here, in this exaggerated shape, this deflected geometry, in this deformed shape, in this geometry right here, I would have the end moments associated with this dotted blue line. If I look, end AB is concave down. So that would be associated with a moment that goes like this. And end BA, or end B, is concave up. And there I would have a moment that's associated like this. So I'll call this for now MAB. And I'll call this MBA like this. There would be also end shears, which I can solve for in terms of MAB and MBA, which I'll call VAB on the left and VBA on the right. And just like we did before, following our process, I can use equilibrium to solve for these end shears so that I can draw my shear and moment diagram in terms of MBA and MAB. And here, if I apply some of the forces in the vertical, this would just tell me that VBA equals VAB. Yay! And if I take moments about an end, I take moments about A, some of the moments about A equal to 0, like this, I would get MAB plus MBA minus VBA times L equals 0, and this would tell me that VBA is equal to MAB plus MBA over L. Alright, so no big deal. And now, just like before, and you don't have to draw the shear moment diagram if you noticed. If we're going to use a double integration method, once we have these end shears and end moments, we could just cut and find a moment function. But here, I'll show you this diagram here, and this time without the exaggerated, deformed, or chord rotation. Alright, so here, and here, in terms of MAB and MBA, I would have, alright, so far so good. Shear diagram, let's see, the loading is 0, so this is going to be constant, and it's just going to go straight across. And my moment diagram is going to start from the bottom and go to the top, or go to MBA, from MAB to MBA. Alright, so there's my shear moment diagram, which really just tells you, okay, you can use a double integration again, or some method that you want to calculate this internal end moment, these MAB, MBA, in terms of psi or delta, really. Now we are going to apply the double integration method to relate the member end moments. And so for that, I want to come up with a moment function. The only discontinuity is at the end. I just need one cut. I'll start from the left end at A. I'll go this way, X, this, and from my free body diagram, or my cut, I want to solve for the shear and moment functions, but I just need the moment function. So if I take moments about the cut equal to 0, applying the equilibrium equations for this cut like this, and M1 is, and there is my moment function. You'll see that when x is 0, I should be at end A. That's negative MAB. And when I put x equals into L here, I'll just get MBA. So life is good. Now I can apply my integration method. So my slope function integrating once from the moment function. Here, this displacement, we have integrating again, displacement function, integrating from the slope function here. And now using boundary conditions, set 4 boundary conditions that are going to be useful for us. And so if I start with the boundary conditions at A, this is at A, the slope at A, which is the slope at x equals 0, is 0, and the displacement at A which is equal to the displacement at 0 is 0. Theta 0 equals 0. So if I plug in 0 here, 0, 0 equals 0 tells me C1 is 0. And then similarly here, if I plug in 0 here, and this equation is supposed to equal 0, so 0, this first term is 0, second term 0, 0, and C2 is 0. These are all 0. Nice. All right, so now we got to relate MAB to delta. Well, the other boundary conditions that are important here are at B, which is when x equals L. Well, first, the slope at B, which is the slope at x equals L, is 0. But the displacement at B, which is the displacement at x equals L, equals, not 0. It is not 0. And the question is it positive delta or negative delta? And so what's important to remember here is you got to go back and recall your double integration method a little bit here. You have x, and in your local coordinate system, when applying the double integration method, a displacement upwards was considered a positive displacement. So we might have a magnitude delta at end B, but in terms of the local coordinate system, we have negative delta. Yes, like that. All right. Delta represents the magnitude of that relative displacement. The negative is associated with the local sign convention for the member. And if you are able, one of the most difficult things about slope deflection and displacement methods and matrix structural analysis is the changes in the positive sign convention. So if you can remember what the difference is between global positive sign convention, internal loading positive sign convention, and I'm going to say this again, in your slope deflection sign convention, and then you can remember your local coordinate sign conventions as you apply various methods, then wow, if you understand all that, you're doing great. You're doing awesome. But now I'm going to apply these boundary conditions at B to solve for these relationships. MAB as a function of delta and MBA as a function of delta. And so if I apply that first boundary conditions, the slope at B, this tells me that EI theta at L, when x equals L, this is equal to 0. So if I plug in some letters here, so if I plug in L for all the x's, and if I simplify this, yes, and whoa, guess what that tells me? This is going to tell me that MAB equals MBA. And if I use the other boundary condition for the displacement at B, and so here in the displacement boundary condition, the displacement at B is equal to, maybe there's a little bit too much to write, but nonetheless, VB of L, which is equal to negative delta. So EI negative delta, and this is equal to, I'm going to plug in L for up here, wherever I have an X, this will be M. Yes, and I know that MAB equals MBA, so this is making things a lot easier. This relationship, I will get a negative MABL squared over 6. And this would tell me that MAB is 6EI over L squared times delta. Yes, the positive result just means that the direction I drew that internal moment AB is good. And just like before, and because MBA is the same, MAB is also MBA. like this. All right, so if you're still with me, you deserve a freaking medal. All right, and we've accounted for now theta A, the rotation at A, the rotation at B, and this chord rotation in terms of this relative displacement delta. The only thing that we're missing are the end moments induced by the loading beyond the member itself. The last part that we have to add, it's the member end moments due to member loading. And here, this would be the applied load. So is it a distributed load? Is it a concentrated load? Doesn't really matter. But according to the principle of superposition, we've already accounted for the rotation at A, the rotation at B, and this relative displacement. And so we have to make sure that whatever model we use for the member end moments due to the member loading, we have to have the slope at A equal to 0. We need the slope at B equal to 0. And we better not have any relative displacement. All those. So that really screams to us a fixed member. Whatever the loading is on the, I don't know what the loading could be, but let's say it is a distributed load that we had drawn initially, or and it doesn't even matter if it's uniformly distributed, linear, and in any case, it's going to result in internal moments at the ends here, at end A and end B. And we call these fixed end moments because the ends are fixed and the moments are there. If you can imagine, if you did the analysis here, you'd have a moment and a moment here associated or caused by this distributed loading. What you'll find is that there are a bunch of tabulated values for fixed end moments. So if you just Google search fixed end moment tables, you'll find these everywhere. And if you have a textbook, they're probably on the inside cover of your textbook already. And you'll see, like for instance, if it's a uniformly distributed load, they'll tell you that this right here, and it's WL squared over 12, and this is WL squared over 12 in this case, just because the loading is symmetrical. In the member, if you were to actually cut it out, if we're using the slope deflection sign convention, we would say the fixed end moment AB, because it's going counterclockwise, is negative WL squared over 12. And here, because the fixed end moment BA is going clockwise, is a positive WL squared over 12. So the biggest challenge really is using the tables to interpret how they would be applied to your member. And again, these fixed end moment tables will have all manners of loads on the member and tell you what the support reactions are for a fixed beam. And now we literally want to sum it all up. So we took this crazy looking deformed shape and loading right here with whatever load you want to apply to it, and we broke it up into a bunch of parts. All right, we broke this thing up by principle of superposition. We started with theta A, then we added on model for theta B, the member end moments associated with a rotation theta A, with everything else being held constant. Then we broke it up into a model with theta B and everything else being held 0. Then we said, okay, let's look at the relative displacement. So we're this delta, and we had everything else. Last but not least, we had to include the member end moments due to the applied loading, but with everything else being held 0, which gave us a fixed beam. And whatever that loading is, those end moments would be considered positive if they cause a clockwise internal moment like this. So this is it in a nutshell. This is what we did. We took this and we broke it up into 4 parts. And now we just need to add them all up together. This moment AB right here is equal to the sum of everything on the left here. And just like before, our positive, as part of our slope deflection sign convention, end moments going clockwise are positive. And so when I look here, I would be including MAB would be equal to the sum of 4EI over L times theta A plus 2EI over L times theta B. And then here, MAB for delta, for this relative displacement, is going counterclockwise. So this is going to be a negative 6EI over L squared times delta plus whatever the fixed end moment is at end AB. And then similarly adding up for end MBA, here this would be 2EI over L theta A plus 4EI over L theta B minus, again, minus because here this MBA over here for delta, for this relative displacement, is also going counterclockwise, plus FEMBA. And these are the slope deflection equations. And in generic form, what you can do is, here, if I look at the form of these equations, I'll notice that here, like MAB, from the perspective of A, is 4EI theta A plus 2EI L theta B minus 6EI over L squared times delta plus FEMAB. All right. And then you'll see kind of like the reverse right here. If I rearrange or if I do some simplification, you'll notice right here, I could do generically the moment of near. So if I'm looking at AB, A would be the near point, F or B would be the far point, and this would be like 4EI over L theta near plus 2EI over L theta far minus, let's see, 6EI over L times delta over L, which is the chord rotation, plus FEM near far. And this would work whether I'm looking at AB or BA. I would get the same result, right? Okay. And what's more, I could do some simplification here even more. And you'll notice that I put here, for delta over L, I can substitute psi here, and then I can probably even factor out a 2EI over L for the first three terms. My final equation can be expressed as 2EI over L times 2 theta near plus theta far minus 3 psi plus the fixed end moment near far, NF. And depending on the textbook, they'll use AB. Some will even use IJ. All right, so they'll just say beginning and end, but you just have to remember what is your beginning and what is your end, or what perspective you're looking for or from. And so which end of the beam are you looking at? And this is my slope, or these are my slope deflection equations for a member. All right, so if you made it through, you are a superstar. And here, I think this one probably image, this right here, this will sum it all up in one single page. Yes, 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 yes. All right. Hopefully you enjoyed it. I don't know how long this is, but it's probably like an hour. All right. Or maybe 30 minutes after I edit it. Take it easy. Start your free.